Good morning, ladies and gentlemen, and welcome to this presentation on catalyst characterization. I'm Christian Hulteberg, and I will be giving you this presentation today. It's the second to last in our webinar series. Hulteberg Chemistry Engineering is a small engineering firm specializing in heterogeneous catalysis. We cover the full chain from research, development, upscaling, and small volume production. And we can help anyone from idea to implementation. Today, we'll start with a brief introduction, then we will go on and talk about characterization of catalysts. We will divide the presentation into fine particle analysis and spectroscopic methods. And after the presentation, you will have a much clearer view of what I mean by these two. Then at the end, there will be some concluding remarks and, as usual, tips for further reading. The purpose of doing any kind of characterization of a catalyst is to map its properties. It can be for research purposes, it can be for quality control, post-mortem analysis, what went wrong, try to figure that out. We use different methods depending on what part of the catalyst cycle we're interested in evaluating. So if we look at the actual cycle, we have a molecule diffusing from the bulk to the surface of the catalyst, continue diffusing inside the pores and adsorbing on a surface, reacting, desorbing, pore diffusion out, and bulk diffusion out through the stagnant boundary layer. So step 4, that's the surface chemisorption. Step 5 is the desorption, and then between 4 and 5 we have the formation of reaction intermediates, which we can also be interested in seeing. The steps 1 through 3 and 5 through 7 are determined by diffusion. So if we look at these methods, or these two categories of methods, we have fine particle analysis, which is mainly related to the transport issues, particle size, density, porosities, dividing the material into micro, meso, and macropores, for instance. But we also do include chemisorption here, which is related to 4, 5, and the reaction. Spectroscopic methods mainly look at steps 4, 5, and the reaction, but you are also able, in some instances, to derive information for the transport steps. But let's get started with the fine particle analysis. Here is an overview table of the ones we will be covering today. We have various ways of measuring density. We have mercury intrusion porisometry. We have physisorption, which is normally interpreted with the BET equation and also therefore referred to as BET analysis. We have chemisorption. You use different probes to get different information. For density, you can use helium or fine powder. You can use mercury, you can use nitrogen, krypton, or argon to get the physisorption done. And for chemisorption, you can basically use a broad range of materials. In all these samples and all these analyses, you'll get an average of the overall material used. So you won't be able to see any specific small parts of the catalyst. It will be a sum of all material in the sample tube. In all cases, the sample preparation is easy to medium, and they're all quantitative. And for some of them, you get sample degradation. For instance, for mercury intrusion porisometry, the sample is spent after analysis. So do the other non-destructive sampling first. With respect to ranges, mercury intrusion porisometry gives you pores from 3 to 360,000 nanometers, and the physisorption from 2 to 50 nanometers, but with better resolution than the mercury intrusion analysis. So they overlap quite well. The lower limit depends quite a lot on the probe used and the material for physisorption. So it's less than 2, but it can also be significantly less than 2. But let's start with more general points. These are all surface-related methods, and the key accessibility here, or the key point here, is that you only get information about the actual surface that is accessible for the molecules. So you won't get information about parts of the catalyst that are completely enclosed, which you can get from analyzing the material using spectroscopic methods. We use adsorption with different probe molecules, or we relate on physical phenomena. It's an important distinction in this field also between physisorption and chemisorption. But let's start with measuring particle size. Particle size is the first thing that we can measure on a catalyst. It relates to measuring the size of a powder. There is a wide range of techniques. This is an important area for many different reasons, not just in catalysis. We can use Taylor dispersion analysis, DLS, nanoparticle tracking analysis, resonant mass measurements, laser diffraction, spatial filter velocimeter, and automated imaging. And the first one, Taylor dispersion analysis, is not applicable in our case. The dynamic light scattering uses light to scatter and differentiate particles during Brownian motion. And nanoparticle tracking analysis uses, again, light scattering, as well as the Brownian motion in the liquid suspension. Resonant mass measurement use the influence of particles in the suspension, as well as the resonance of a mechanical device to determine particle size. We have laser diffraction using the angular intensity variation in light scattering. And spatial filter velocimeter uses the shadows cast on an array by passing the particles through a laser beam. And finally, automated imaging just takes a lot of picture of a sample and finally gets us a statistically significant distribution of the powder. And the distribution of the powder is important when it comes to the next field, which is density. Density is another thing that we measure on the macro level normally, but we may also be interested in several different densities. The density of a powder is what we refer to as the tap density. So it's the bulk density, the density it will have when we pack it in a container for shipping, for instance. We have the envelope density, or the geometric density, which is the density of the material if you assume them covered by a layer. And then you have the absolute density, which is the density free of all pores and just referring to the material in the walls of the catalyst material. So the absolute density is larger than the envelope density, and the envelope density is larger than the tap density. Absolute density, we measure the volume of the material without any pores within the sample material. And for all of these cases, density is defined as the sample weight divided by the sample volume. We measure the absolute density by helium in a pyknometer, but we can also determine it using water or mercury intrusion. And since we use helium in the pyknometer, it's normally referred to as the helium density, or normally it's also sometimes referred to as helium density. The envelope density takes a slightly different approach. It measures the volume of the particles, but ignores the porosity inside. So think of it as covering the particles by a thin layer of wax and then calculating the density by using the weight inside the wax layer. And again, this can be measured by powder pycnometer or with mercury intrusion. Tap density is measured by filling a container with the sample material, then tapping or vibrating the container to achieve as close to optimum packing as possible. Vibrations are oftentimes just lifting and dropping the container from a controlled distance, a controlled number of times. And that tells us that the tap density is not just material properties, also how we do the testing will influence the results. So that was that on density. The next analysis method is mercury intrusion porosometry. This is a method for measuring macropores. Unfortunately, it's the only one, and unfortunately we have to use mercury, which of course should be minimized. So we use this method when it's motivated, much more so than other characterization methods. What we do is add a pillar of mercury on top of a sample, and by increasing the pressure, we physically force mercury into smaller and smaller pores. And the volume for each pressure increase gives us the pores in that size range. It's operating at very high pressures, so 414 megapascal, for instance, 60,000 psi or 4,000 bar, something like that. So we really have to work with mechanically strong materials, so no soft matters, no easily collapsible structures. It's perfectly fine for ceramics, but for native materials like wood, etc., it's not very practical. It will give you, however, a very good information on pore size and pore volume distribution, ranging from 3 to 360 nanometers, so not the smallest of the pores, but up towards particle size. That's 0.3 millimeters, so rather large particles. We use the Washburn equation to calculate the diameter of the pores. So you have 4 times the contact angle between the material and the, 4 times the surface tension between the material. And this cosine is the angle is the contact angle between the surface and the mercury. And this only applies for materials that are non-wetted for mercury. So you have to have a contact angle lower than 90, so it cannot wet the material. Then you increase the pressure, and the higher the pressure, the smaller the pores we can force the mercury into. And this is a representation. We apply pressure, then mercury goes into the pore once we've applied high enough pressure. And since mercury is conductive, we actually have a very nice way of measuring the volume that goes in by measuring the conductivity of this stem part here. So the first thing that happens is that we remove all gas and water inside the particle to be analyzed by evacuating it. We fill it with mercury, and then we increase pressure and in stages, and we get a pore size distribution. And they normally look something like this, that you have the pore diameter on this axis, and then you have the intrusion volume, the millimeter or milligram of mercury that can be intruded per gram of catalyst, and it gives you a distribution of pores. And in this particular case, we've looked at a fresh sample which had quite large meso porosity, and then by performing the reaction we remove the finer particles here, and we also see that after reaction the particle diameter, which is represented by this part here for the fresh sample, has grown, so there's actually been a formation of solid carbon on the outside of the particle. So that's the type of information you can derive from the data. The pore area can then be calculated by simple geometric relationships as well as the pore length, and we can also obtain information on density as well as tortuosity, so how much the pores are turning and twisting inside the material. So quite useful technique, but it should be used with caution due to the use of mercury. Physisorption is also used for measuring surface area as well as pore volume and pore size distribution of different materials. Here we work in a smaller size range, 2 to 50 nanometer pores, and we use different gases at different temperatures. Usually we use nitrogen as the probe gas, and we do the analysis at liquid nitrogen temperature. So nitrogen, most common probe. Argon is used for microporous samples. For really small pores, the dipolar nature of nitrogen interferes with the analysis. And for low surface area samples, less than 1 to 2 square meters per gram, we use krypton because it has much lower vapor pressure at the liquid nitrogen temperature than nitrogen, so any change will be much larger for krypton. Just removing one molecule from the gas phase to the surface will induce a larger change. And what you do is you cool down your sample, then you inject a known volume of gas into the sample holder, and then you measure the pressure change very precisely. And for the first part you get the monolayer, so the first coverage of the material by one single layer of the probe gas, and then after that, when you increase the amount of gas, you will also get condensation in the pores, and you get results looking like this, where you have a first shoulder here, which is representing the monovolume layer. You get filling of the pores, and you get a difference between adsorption and desorption due to the nature of the pores. We'll come back to that in a sec. And then this can be translated also into a differential plot, giving you the pore diameter as a function of, or the adsorption or the quantity volume as a function of the pore size. And we'll just stop here for just 1 second and talk a little about pores. There are a few different types of pores. You have open pores, which is A here, has open communication to the surrounding. We have closed pores, which means that it's completely encapsulated in the material, and these pores will not show up on this type of analysis. They will, however, show up on other, for instance, X-ray diffraction that we'll talk about later. And then you have also cylindrical and open-ended pores, which are open in both ends. And depending on what type of materials we analyze, we get different standard or different isotherms. And we've defined them into 6 standard isotherms, where number 1 here is for solids with micropores. You see this large shoulder here indicates the micropores. Number 2 and number 4 are for solids without pores or with rather large pores. Type 4 here, oh sorry, 6 here is for non-porous solids with almost uniform surfaces, which is really rare. Type 3 and type 5 have higher affinity between the gas probe molecules than between the probe molecules and the material, and that makes them useless to us in this context. So that means that 1, 2, and 4 are the ones that we normally consider in these type of measurements. And that's basically what's on this slide. So we'll skip that. So what then? Now we have an isotherm. What do we do with it? Well, we use some kind of theory to describe the isotherm. There are many different isotherms available. Langmuir, Henry, Freundlich, Temkin, but the most used one in this context is the Brown-Auer, Emmett, Teller, or BET, where the volume, physisorb or chemisorb, can be described by this equation, which basically takes the monolayer volume, multiplies it by a constant, which is down here, and then takes the pressure divided by the surrounding pressure, or saturated vapor pressure. And then you can calculate the monolayer volume. But to calculate the monolayer volume, you also have to make some assumptions based on the close packing of the area that one molecule occupies. So the close packing factor is calculated like this, and for different probe molecules, they end up in the 0.2 roughly square nanometer size range. Then what more you can do is you can calculate the pore size distribution using the Kelvin equation, which is for pore condensation, and you can then follow a method suggested by Barrett, Joyner, and Hallenda in 40s, I think, and end up with a nice plot of the full distribution. You start from the high value, and then you imagine the isotherm as a series of steps going downwards, and then the amount that you lose in each step represent the volume of the pores emptied. And this was probably a very tedious activity when it was developed, but today we have automated computer systems that do this for us. And we also need to make assumptions. So we need to decide if we think the pores are straight cylinders or slits for plate-like materials, or if they're cavities formed by touching spheres. Sintered objects are quite common in our world. And these assumed or these geometric shapes of the pores actually explains the difference between the adsorption and the desorption isotherms. For the adsorption isotherms, when the pores are emptied, it's just the radius of the actual pore that will determine the condensation of the liquid in the pore. But when we do desorption, we will actually only have vaporization from the pore mouth, the openings of the pores. So the difference between the adsorption and desorption isotherms gives us information about the actual openings and the actual pore sizes of the material on average. Again, this is an average method. And I normally use the desorption isotherm because to me the pore mouth restriction is the one that we need to consider when it's about diffusion and stuff like that. But other people may have other opinions on that. So you should get your own opinion on this topic. We'll now turn to chemisorption, which is used for determining certain aspects of a catalyst surface. It can be the acidic sites, it can be basic sites, or it can be the metal surface area of a supported metal catalyst. We perform this at a controlled temperature. We inject small controlled amounts of gases, and we measure a change in pressure again. Then, in this case, however, we will get a reaction with the material, and we'll first do one analysis with the sample when we have no material on the surface, and then we will redo the analysis immediately thereafter on the same material to be able to differentiate the chemi and physisorbed material, and then the differential should be a straight line between those two and give us the volume of chemisorbed material. One important factor, however, is when we want to translate these results into, for instance, a surface area of a material, and that's how the probe molecule will adsorb on the surface, how it reacts. Is it reacting and adsorbing just on the C, on the carbon monoxide? Are there two bonds, or does it dissociate? All of these means that the molecules will take different space into account, which will then be translated into our calculation. So we need to combine this method with either our own analysis, for instance FTIR, of the adsorbed species, or with literature search to see what we can expect with respect to adsorption. But once we know the stoichiometric factor, we can calculate the number of sites. We have the adsorbed amount of gas, we have Avogadro's number, and we have the stoichiometric factor. And if we divide that by the molecular volume, we get the number of sites on the surface, and that can be used to calculate the dispersion. So amount of total metal divided by the surface area, or measured amount of metal, gives us how large fraction of the metal is actually available for being in contact with gases. We can also use the average monolayer adsorption area with this equation. Again, it's the stoichiometric factor, it's the amount adsorbed, it's Avogadro's number, and then it's the cross-section area to calculate the actual area, square meters per gram of a metal. And by assuming, for instance, spherical particles, we can calculate the diameter, average diameter of a particle. We can also use it to determine heat of adsorption. Then this cross-section area is dependent on what type of materials we're analyzing, but in general it's somewhere 6 to 9 square meters per atom, 10 to the power of 10 to the power of minus 20, sorry about that. And here you have the most common culprits in catalysis. Chemical or chemisorption can also be done in a temperature program mode, and in this case we call it dynamic chemisorption. And we can do, for instance, temperature programmed reduction, oxidation, desorption, or reaction, and this will give us nice fingerprints for comparing within a series of measurements. We can look at, for instance, the reduction of different metals on a surface and what happens when we mix metals. We can show very nice synergistic effects. For instance, when you have a combination of nickel and molybdenum on a surface, we actually have a lower, about 100 degrees lower reduction temperature for the mixture than any of the two individual metals. We can also use it for calculating heats of adsorption, and then you will have to do the measurement at different temperature ramps. So the beta here is the temperature ramp, the heating ramp, and then you will plot it and it will give you a straight line if you assume first order kinetics, and you can then calculate the desorption, adsorption, reduction energy based on that. That was the fine particle analysis. I will now spend a few minutes talking about spectroscopic methods. And spectroscopic methods is basically firing energy on a sample and seeing what happens. It can be shooting X-rays on a sample and having electrons or photons coming back. It can be shooting electrons and seeing what happens with the electrons. And I've tried to, and this is a huge area, and there is no claim to being complete in this way. It's just it's an overview. But this table here tells us what different beams can be used. It's neutrons, ions, electrons, photons, thermal effect, magnetic, sonic effects that can be used. And then also what happens, what is, which materials are, so this is what is being shot in, and this is what is coming back out of the sample. So if we have electrons and we get electrons back, electrons getting electrons back, diffraction, electron microscopies, and other materials. If we shoot photons and look at the electrons, we get X-ray photoelectron spectroscopy, for instance, etc. And if you look at the probes, they are different in energy, and with the different energies, we also get different possible techniques. And the lower the energy, the less severe will the penetration be in the material. And that also comes back into the analyzed thickness. So the analysis thickness is how deep we are penetrating the sample, but we also have size of the actual beam, which gives us, translates into an area analyzed. And if we look at some, for instance, Raman spectroscopy will analyze quite deep in the material, which means it's a bulk method, but it will be quite specific to a narrow area. So you could actually, in theory at least, sample different sites. Some of these are possible to do quantitative measurements, and some definitely. Then you can, for some of them, change the gaseous atmosphere. That means having something that resembles a reaction atmosphere around the sample. Then you have temperature ranges, and here's the information you get. So from Raman you get functional groups, and you can have adsorbing species analyzed as well. Some of them are slightly damaging to the sample, while others are not. And that's molecular and resonance spectroscopy. We have electrons here. Some of them are surface techniques like XPS, AES, EELS, SIMS. And then X-rays, this is for more bulk type analysis, and some of them are vaguely quantitative, some are very quantitative, and in some cases we operate under high vacuum, making having gaseous atmospheres difficult, while others do not. It all depends on the strength of the X-rays used. So the stronger, the more the energy, the deeper into the sample will penetrate, but we can also tolerate gaseous atmosphere. And here we look at a few atom layers. Here we look at the bulk of the materials. This is also a field which has probably the world record in abbreviation. I've summarized as many as I could figure out in these tables here, but there's no claim to be concise, and we won't go through all of them. But please use it as a reference and look up any abbreviation. And if you find new ones, just feel free to shoot me an email, or if I forgot one, and we will be complementing this section. We'll talk about a few of them. One that I've used and find quite useful is X-ray diffraction. It measures the scattering of photons when you shoot X-rays at different angles at the surface, and then at certain angles you get signal amplification due to interactions or synergistic interactions with the material. And the nice thing about this method is that it's really inherent to the material, so you get nice fingerprint of the material that you can take and go to a database, and you can identify the material and the crystal structure that has formed. Use it on powders or on single crystals, and it has to be crystalline. And the drawback is that you can't see low concentration of materials unless you spend an infinite amount of time doing the analysis. So maybe 1 to 10% is our visibility limit. And the spectrometer looks something like this. You have a laser and a detector, and you vary the angles from low incidence up towards 90 degrees, and you get a sample or diffractogram looking like this, where you have certain peaks reinforced at different areas. And when I started, you actually used tabulated values in books. Then you started with the highest peaks, giving it 1 as an intensity, and you related the other peaks to that, and you used it for looking it up in a large book. And what you also can do is use it for calculating particle size. So if it's an infinite crystal or large crystals, you will get a nice reflection between the two lattice planes using this equation, where lambda is the wavelength, and this is the incident angle. But for small crystals, these will lead to a flattening of a curve, getting it less sharp and less defined, which will be can be used for calculating the crystal thickness using the Debye-Scherrer equation. Electron microscopy. Here we have two different types, scanning and transmission. It uses a very highly concentrated electron beam and looks at the surface. And for SEM, we use the electrons that are bounced back from the sample. TEM, we use the electrons that pass through the sample. We get different resolution, and with TEM we get down to the molecular level. SEM is more for overview pictures, and you can do other things whilst you do it, like elemental mapping, and to get an idea of the distribution of materials. You get very nice pictures for including in papers, and you get a good idea of what the material looked like, at least for the samples that you analyze. I normally say that electron microscopy is like analyzing the country of Sweden by looking out the window that is closest to you if you are situated in Sweden. But you need to look out of a lot of windows to get a really concise overview of the country. So there is some statistical work needed, and you need to take quite a lot of pictures to be able to make statements on the material as a whole, but it's a very useful tool. Infrared spectroscopy. Here we look at the surface chemistry. We can send in different probe molecules like CO, ammonia, and it gives you the nature of the environment around these probe molecules. So we basically can see how these probe molecules have absorbed and what species they have reacted with. And then we can match them against literature data, looking at symmetric and asymmetric elongations. We can use different types of shearing or rotation around the planes, and also oscillation and torsion out of the plane. Raman spectroscopy is rather similar to IR, using a different light source. Again, shooting the sample with a monochromatic light source, and then we measure the scattering of the light, and we get a fingerprint of vibrational energy which is specific to the material. But we can also use it for identifying acidic sites, like sending in pyridine, and looking at how many molecules of pyridine is absorbed and how they're absorbed. We can actually differentiate between Brunsted's and Lewis acid sites. And we can also use it for surface studies, like looking at how benzene adsorbs to the catalyst surface. We've used it for characterizing tungsten, looking at how the tungsten crystalline structure changes from triclinic up here and fresh to monoclinic on increasing temperature of pretreatment. Finally, X-ray photoelectron spectroscopy uses low energy X-rays, and we use it for identifying surface atoms and their concentrations. We can determine, for instance, the degree of oxidation or the electronic state of various elements. And we can also follow sintering of the support metal, since it's really selective only to the outer atom layers for all species except for helium and hydrogen. So to summarize, characterization is important for understanding the phenomena of catalysis. It aids and helps in understanding both the transport properties as well as the chemical properties. The first part is mainly determined by the fine particle analysis, while the chemical properties is more towards the spectroscopic analysis toolbox. And we need to combine methods to make sure that we have coherent conclusions. So surface areas of the materials can be calculated both using physisorption of nitrogen as well as from X-ray diffraction or chemisorption. The further reading, catalyst characterization, physical techniques for solid materials. There's a very nice book on fine particle analysis, analytical methods in fine particle technology. Then, if you're new to the subject, there's an introductory book. You can also look at what to do with industrial catalysts. And then there are specific books on specific methods, like temperature program reduction and infrared spectroscopy of absorbed species. And with that, I would like to thank you for listening yet again, and I hope to see you soon. Thank you.